Hello everyone. In today's video we are going to be talking about spring potential energy and work. As you already know, there are two main kinds of energy: kinetic energy, which is the energy of motion, and potential energy, which is energy that has the potential to become kinetic energy. There are many different kinds of potential energy, such as gravitational potential energy, which results from the force of gravity between two objects, elastic potential energy, and internal potential energy, which is released in forms of heat, light, vibrations, sound, and many other forms. The change in a system's energy is its work, and its change in energy, or work, over time is its power. Today we are going to be learning about a special kind of elastic potential energy called spring potential energy. Spring potential energy is the potential energy of a system that results from the stretching or compression of a spring. Spring potential energy is a specific kind of elastic potential energy, which results from any elastic material being stretched or compressed, such as a bungee cord or a slingshot. In order to understand spring potential energy, we first need to understand the force of a spring itself. As you probably already know, squeezing or stretching a spring, it gets harder and harder the farther away you want to move it from its equilibrium, which is where it rests when no force is acting on it, which means that the force it takes to move a spring is relative to how far it's being stretched from its equilibrium, or the distance at which it's being compressed or stretched. You also know that some springs are easier to squish or stretch than others. For example, a large industrial spring is almost impossible to squeeze with your bare hands, whereas a small spring you can easily squish. We represent this in our equation using a constant called K, which represents our spring constants. And all that means is how stiff the spring is. So that is our spring constant K. You also know that the force at which a spring pushes or pulls back on you is opposite in the direction the force that you are applying on it. For example, if you're pushing on a spring, the spring is pushing back against you, whereas if you're pulling the spring is pulling away from you. This is why we put a negative sign in front of this equation, because the force being applied by the spring is always opposite the force being applied on the spring. You may ask yourself why we need to know the force of a spring in order to know the spring potential energy of a system. Let's look at it using an LOL diagram. Here we have a spring resting at equilibrium. It's not compressed or stretched. It's just sitting there by itself. And here we've applied a force normal to the spring to cause it to compress. Now let's analyze the energy that's happening in each of these situations. In the first situation, the spring is not moving, so we have no kinetic energy. The spring is resting on the ground, so we have no potential energy of gravity. It's not compressed, so we have no elastic potential energy yet. And we also have no internal potential energy. In our second situation, when the spring is compressed, we have no kinetic energy because the spring isn't moving, it's staying where it is, but it's compressed. We still have no potential energy of gravity because the spring is still on the ground. But we do have some elastic potential energy now because the spring is pushing back, is going to be able to push back and translate into kinetic energy once we release that force normal that is pushing back on the spring. And we still have no internal potential energy. So, as we can see, there's been a change in energy in the spring system from before and after the push, which is equal to our work, is equal to our potential energy of the spring. And this work is caused by our force normal. So, we know that work is equal to the force times the distance at which it is applied. Therefore, in this situation, our spring potential energy is equal to the force times the distance at which it is being applied. So, in order to find our spring potential energy, we are going to need to find the average force in our original situation. Let's draw out a situation of a spring on a wall attached to a box being compressed by a force normal, let's say. And I'm going to use these lines down the middle of the box to indicate the center of mass of these boxes. And let's say that this is at equilibrium, and this is when the spring is being compressed. Let's say the center of mass of the box at equilibrium is x equals 0. So the force spring in this situation is F is equal to negative k times delta x, which is 0. Because our original position is 0 and we have moved 0 meters in either direction. In our second situation, our center of mass has changed by delta x. So our force in this situation is equal to F equals negative k times delta x, which we can see is our formula for that. But we need to find the average force of this situation. So our average force is equal to our initial force initial, plus our force, let's call it force final, even though it might not necessarily be what actually happens in real life to be the final force, divided by 2. So we're taking the average of these two forces. So our average force is equal to 0, because anything times 0 is 0, and added to k times delta x. And we're going to negate that negative sign for right now because that's merely an indicator of direction. And if you look at the problem itself, you should be able to figure out well enough where the direction of this is. So divided by 2. So our average force is equal to 1/2 times k delta x. Now we can plug this average force back into our equation for spring potential energy. So our spring potential energy is equal to 1/2 k delta x times delta x, or 1/2 k delta x squared. And real quick, it's important to note that the spring as a single object does not have elastic potential energy, but the spring as a combination of all these small little molecules that are pushing and pulling against each other does, because a spring is actually a system of smaller molecules and it's not a perfect object. Most, if not all, objects are not actually perfect objects, but for the purposes of physics, we tend to treat them as them just to make our lives easier. So now let's rewrite that on our page that's actually supposed to be dedicated to spring potential energy in this little bit in the corner that we can fit it. Our spring potential energy is equal to 1/2 k delta x squared. No. Should do that. So the potential energy that is stored in a spring when we act upon it in the spring us system, let's say, is relative to how much we compress the spring and how stiff the spring is. And we can see this easily in a little example, such as in an LOL diagram. I've drawn out a situation that includes a spring being compressed by a box, and the box is not moving when it hits the spring and starts to compress it. It's dropped, quote-unquote, from rest. So let's go through the LOL diagrams of these situations. In the beginning, the box and the spring aren't moving, so there's no kinetic energy of there's no kinetic energy. There is potential energy of gravity in this situation in terms of the box, because the box is going to be pulled to Earth. And even though the spring is in its way, because the spring is going to be able to compress rather than just staying still, we still have potential energy of gravity between the box and the Earth. So we're going to draw a little bar for potential energy of gravity right here. We have no elastic potential energy yet because the spring has not been compressed, and we have no internal potential energy. Instead of going to the half compressed situation, let's go ahead and go to the fully compressed situation. This is where the spring and the box have stopped moving downwards and are in fact about to start moving upwards. So there's an instantaneous point in time in which the box and the spring are not moving. So because they're not moving, they have no kinetic energy, And because they're as close to the ground as they can be, there's no potential energy of gravity. However, because the spring is compressed a lot, we have a large amount of elastic potential energy. And in fact, because we have no internal potential energy, this elastic potential energy is going to be equal to the gravitational potential energy we had before the spring was compressed, because energy is going to be conserved. In the half-compressed situation, the box and the spring are moving, so we do have kinetic energy. We also have potential energy of gravity, and by half-compressed, I should have specified this earlier, I mean partially compressed. I didn't want to create any confusion with that. I'm sorry I didn't do that earlier. But anyway, so we still have potential energy of gravity because the box still has some height to drop before it is completely as close as it can be to the Earth. We have potential energy elastic because the spring is being compressed. So let's draw that in here, and we still have no internal potential energy. So all three of these categories, kinetic energy, potential energy of gravity, and potential energy elastic, when you add them together are going to be equal to the gravitational potential energy before the spring is compressed, or the elastic potential energy once the spring is fully compressed. And as you can see from before, during, and quote-unquote after, the elastic potential energy starts out non-existent and gets bigger as the spring gets more and more compressed, which we can relate back to our equation. As the spring gets more and more compressed, as delta x gets bigger and bigger, our spring potential energy goes up. Now let's try out an example problem. Example problem number 1. If a spring compressed 0.5 meters launches a 4 kilogram box to give it an instantaneous velocity of 15 meters per second, what is the spring constant? Assume a horizontal spring and no friction. Let's use an LOL diagram to represent this. So, we are going to have the spring, box, and earth system. And if you want to draw a little picture to represent this, it would be a spring compressed against a wall with a box that is going to shoot it at 15 meters per second. So we have our kinetic energy, potential energy gravity, potential energy elastic, and potential energy internal. And here we also have kinetic energy, potential energy gravity, potential energy elastic, potential energy internal. So, because the spring is going horizontally, let's say it's on the ground, we have no potential energy of gravity in this situation, so I'm going to go ahead and mark both of those off. Before the spring is let loose, it's going to have no kinetic energy because the box and the spring are both going to be held and waiting for the spring to release, and they're not going to be moving. We are going to have some elastic potential energy because the spring is compressed. We are going to have no internal potential energy. However, once the box is released, it's going to be moving. So we're going to have some kinetic energy. The spring is going to no longer be compressed, so we have no potential energy, and we still have no internal potential energy. So all of our elastic potential energy from when the spring was compressed is going to be translated into kinetic energy once it releases. We know that our kinetic energy is equal to 1/2 mv squared, which in this situation is 1/2 times 4 times 15 squared. We also know that our spring potential energy is equal to 1/2 k delta x squared, which in this case is 1/2. We don't know our spring constant yet, so I'm going to leave that as k, and our delta x is 0.5 meters squared. So now what we have to do is solve this equation. Simplify this real quick. This turns out to be 550 joules, and this is going to be 0.125 times our spring constant. And we know that because our elastic potential energy is the same thing as our kinetic energy in this situation, we can set them equal to each other and say that 0.125k is equal to 550. So now we just need to divide by 0.125 and we get that k equals 4,400 newtons per meter, which is a lot, but that's what we got. Let's do another problem. Example problem number 2. The graph of a spring's force versus its distance compressed is shown below. What is the significance of its slope? What is the significance of its area under the curve as well? Let's start off with the slope of this line. We can see that it's linear, so we know that it's going to be some kind of constant. And we know that f is our dependent variable, so let's say that f is equal to something times delta x. Because the slope is negative, we know that this has to be negative, and we know that it's a constant because it's producing a linear graph. So let's just say negative c times delta x. Now where have we seen that before? Oh, wait a minute. That's our equation for the force being produced by a spring, now isn't it? And if you think about it, that makes sense, because we know that as we push our spring harder and harder and harder, it's going to push back stronger and stronger against us. So our force is going to be increasing in the negative direction as we compress it more. So the slope is our spring force. Now let's tackle the area under the curve. Let's go ahead and find the area and multiply it out, and then maybe we'll see what happens. So this is our delta x after some period of time, and this height is going to be our force. And we already know that our force is equal to negative c, which is actually k, times delta x. So the area under this curve is going to be equal to the force times the distance at which it's being applied. And that should sound familiar to you because that is actually the work that's being done on the spring, which we know is equal to 1/2 times k times delta x squared, which is also equal to the spring potential energy in this situation. And if you want to work that out, you can also see that the area of the triangle is 1/2 times base times height, which is equal to 1/2 times delta x times negative k delta x, but we can just disregard the negative because, as we said earlier, it's merely an indicator of direction, which is equal to 1/2 times k delta x squared. So the area under the curve is equal to the work being done on the spring, which happens to be our spring potential energy. This is the last of my videos that I've created for my senior exit, and I hope you guys have maybe found this to be an informative experience. Whether or not you liked it, I hope you did, but if you didn't, then I'm sorry. And have a good day. Thank you.